So the subject for the first lecture this morning is detonations. I think it's the only case where detonations. Is this a tablet? Can I have a tablet here, or so I could write on this? But well, okay, fine. Okay, wait, yeah, but
I think you can be seated or stay here, or we project here, and then you can use the tablet on that side. So that's the plan.
Oh, so we're changing the tablets on this side now?
No. Well, do you project on this side and use the tablet on this
side? Yes. Yes. Okay. So this is the only lecture on detonations, and so if you have any questions or anything about, yes, this is what I remember the way it was before. Any questions or anything about detonations, then this is the time to bring them up. I'll try to stop at intermediate points to ask to see whether there are questions that from time to time. So the first thing to look at in detonations is to consider a reaction front. Like this, where there's now a steady flow. So we're going to apply the conservation equations to this steady planar reaction front, if you like, or wave is what they call it, or it's not waving, it's sitting there. So front is really a better terminology. And so the idea then is to look at the conditions upstream and downstream of a thin reaction region, which could be either a deflagration or a detonation, and we'll apply it then in this lecture to detonation. And so the heat release and also the viscous effects and heat conduction effects, diffusion effects occur in this planar region. And the subscript 0 then identifies conditions upstream in this steady flow condition, and the subscript infinity identifies conditions downstream in that condition. Okay, so the first thing to do is to look at the relation for a given set of conditions upstream to find out what the permissible conditions downstream are. And so to do that, you can write down the conservation equations, which we wrote down before. Now, those conservation equations have lots of derivatives in them for viscous effects and things, but those derivatives are going to be 0 because this is considered to be going effectively to infinity in that direction and also in that direction. And so if you look at the conservation equations, then they simplify really greatly when you're just looking for the jump conditions. And so, as kind of indicated there, there's mass conservation. Yes. I pressed something by. How come it's supposed to write here? Oh well, it looks strange. Yeah, I thought I could use this very, very easily, and I'm not using it. It's not doing what I want it to do. Why is it not doing what I want it to do? Suppose I want to erase. Yeah. 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 Okay, now I should be able to write here, no? The trouble is, it's not, the point is not where the point is. right here. The point is way down here. This tablet is misbehaving because the point goes here, but the writing is down there. Did you have?
I will just set it up in 2 minutes.
Oh, okay, okay. Well, at any rate, so let me do it this way. Mass conservation just tells you that the mass flow rate in the upstream condition must be the same as the mass flow rate, mass per unit area per unit time downstream. And so this mass flow rate is called M. So this is the mass conservation equation. Now, momentum conservation equation reduces to simply rho v squared plus pressure. They're the only remaining terms when the viscous effects are gone, and so it's the upstream rho v squared plus pressure is the same as the downstream rho v squared plus pressure. This is steady flow in one dimension. So this is not Bernoulli equation. Bernoulli is for multidimensional flow at constant density, and in that case there's a 1/2 here. But for these steady flows, the equations integrate just to that. And so it's possible then to, when both of these equations apply, just on the basis of mass and momentum conservation between upstream and downstream, just on that basis, without irrespective of energy conservation, whether or not there's any energy release in the combustion process, you can manipulate these two equations. P infinity minus P naught then will be rho naught V naught squared, and you can eliminate the velocity in terms of this mass flow rate and get an expression for the pressure difference divided by since V is m over rho, then V squared is m squared over rho squared, so this is m squared over rho, and so this is 1 over rho, so it's P plus 1 over rho times m squared, and so then that gives you in a plane of pressure and reciprocal density. Reciprocal density is specific volume per unit mass. So in essentially a PV diagram. So in a PV diagram, this gives you a straight line, P minus P naught over 1 over rho infinity minus 1 over rho naught is equal to the negative of this mass flow rate squared. And so this mass flow rate squared then, well, the mass, it determines the slope of a straight line with negative slope in the PV diagram. And so that line is called the Rayleigh line. So it applies to flow with heat addition or heat abstraction, but so flow, but without viscous effects or heat conduction effects and things like that, is Rayleigh line flow. So from this first equation, from these two equations, you can construct a straight line in the PV diagram, the Rayleigh line. The Rayleigh line has different shapes in different diagrams, as you know, but it'll be a straight line of negative slope in a PV diagram. Now, it's helpful in looking at relationships between downstream and upstream conditions to be able to look at an equation that involves only the and I was going to write it down if that rather than use the, but I guess I'll use this instead. Conservation of energy. Conservation of energy is possible to use conservation of energy then to get velocity out of the equations completely and get just a relationship between thermodynamic properties to draw in a PV diagram. That relationship between thermodynamic properties is the Hugoniot equation in the PV diagram. So this is what I just got through explaining. This is the Rayleigh line equation, but you can do the same thing with in the energy equation now, and from in other words, you can write this v squared as m squared over rho squared, okay? And so, but then if you substitute this expression for m squared, then this equation becomes this equation down here, the enthalpy, the final enthalpy minus the initial enthalpy from energy conservation is, because, you know, this 1 plus rho is this sum of these two specific volumes is the sum of the squares that come out when you make that substitution to get this, but then divided by the difference, and so the sum of the squares is the product of this plus this plus this. This cancels, and it gives you that expression. So so that's a result of energy conservation. Now, in these enthalpy terms, it's necessary to include both the thermal enthalpy and the chemical enthalpy. And the point is that now in an exothermic combustion process, the reactants will be at a higher chemical energy state than the products. So that besides the CPT contribution, there'll be a heat of combustion contribution, a difference between the reactants and the products in energy conservation. So when you do that, and use as well the ideal gas law, this enthalpy difference would be the heat released in the combustion reaction per unit mass plus CPT minus T naught. Now, for ideal gas law, the temperature is pressure over density, and so if you substitute the ideal gas law into there, you get this final expression, which I had planned to derive on the tablet, but well, it's here. I'll use the board later then. Yes. So this is the Hugoniot. So this now involves only pressure only pressure and specific volume, and so it's a relationship between it's a purely thermodynamic relationship in the PV diagram, determining the final state from the initial state in that PV diagram. And so the shape general shape of the Hugoniot curve turns out, if you look at that equation, is in the pressure volume diagram is this, and so given the initial state, the final state will be this, would be this intersection of any line with negative slope in that diagram. In that PV diagram, it's nice to get explicit results by making simplifications so you can write down formulas, explicit formulas for Hugoniots, which you can get, but write down. But the main thing is that the final result comes out then, and now this is non-dimensional pressure over initial pressure, specific volume over initial specific volume, PV diagram. The Hugoniot curve has this kind of shape because of the fact that when you have heat release, the fact that Cp over R is gamma over gamma minus 1, which is greater than 1, and so for example, if at a given, if at a point where the final density is the same as the initial density, then this equation is simply gamma over gamma minus 1 is equal to Q, okay? And gamma over gamma minus 1 is greater than 1, and so this thing that multiplies P infinity minus P naught is positive, and so P infinity will exceed P naught when Q is positive. It would be less in an endothermic process where Q is negative, and therefore when you draw on the PV diagram the Hugoniot with heat release, you have a curve which is above the initial state, okay? In the PV diagram, it's above the initial state, and rather, if it were endothermic, it would be low, below. If there were no heat release, it would go through the initial state for the final state. And so then what the thing to do is look at the intersections of the Rayleigh, possible intersections of the Rayleigh line with the Hugoniot curve, and those intersections then will determine the final state for a given initial state. All right. Now there's some slopes, which is a measure of the velocity of the wave, the velocity of the front that things are moving into, for which there's no solution. When there is a solution, there are usually two solutions. Like if the slope is high enough, there's two solutions, or if it's low enough, there are two solutions. Okay, there's a particular point here where the tangent point where there's only one solution, and another point here where there's only one solution. These special points where where the Rayleigh line is tangent to the Hugoniot curve, those special points are Chapman-Jouguet points, and so this is at a higher pressure. This is the upper Chapman-Jouguet point. This is a lower pressure. This is the lower Chapman-Jouguet point. And so the Chapman-Jouguet point divides the intersections into two parts. You can't have a slope this way because that would require an imaginary, that'd be a non-physical situation. That'd be a negative slope. So the intersections on the lower part are deflagration intersections. The intersections on the upper part are detonation intersections. Okay, but there are two kinds. Then, if the change is large, then it's strong. So final states from A to B are strong detonations. Final states from B to C, just to stop here, are weak detonations. Final states from D to E are weak deflagrations. Final states from E to F are strong deflagrations. So they're the four different types of reaction waves that you can have. Seshadri talked last time about laminar flames. Laminar flame is an ordinary deflagration, and laminar flames are usually fairly slow, low Mach number propagation velocities, and that means that the slope is almost zero. Pressure is nearly constant. The first approximation in the laminar flame is constant pressure. So in this diagram, the first approximation to what Seshadri was talking about would have the final state D here, which is it would be nearly. It's laminar flames are weak deflagrations, and we'll be focusing then more on detonations, both weak, strong, and Chapman-Jouguet detonations. These are the jump conditions that take place. Are there any questions about these jump conditions at this stage? Yes?
What do you mean by strong and weak detonation zones, or what physical significance they have?
To see how different they are and when they can occur, we need to look at the structures of the possible structures of the detonation. Okay, and we'll look at that. The basic result that you get by looking at structures and seeing what you have is that deflagrations are mainly weak deflagrations. If you get into turbulent flame propagation, you can increase flame velocities, and you can approach Chapman-Jouguet, but you can't go beyond Chapman-Jouguet, and so you kind of tend to make a transition from deflagration to detonation if turbulent velocities are high enough to give you slopes that will be strong deflagrations do not occur. Basically, there's no solution to the conservation equations for the structure of strong detonations, except for very special chemical kinetic situations that are very rapid reaction rates, and the reactions have to occur on time scales that are comparable or less than collision time scales to have a strong deflagration, and so we just don't have strong deflagration. They don't exist. The most detonations that are real that you find are Chapman-Jouguet detonations. This is the usual situation, Chapman-Jouguet. There are special processes which can go from the initial to the weak branch. A physical example of something that goes from the initial to the weak branch is in wind tunnels. In supersonic wind tunnels, if there's water, if it's moist, the water can condense in a fairly sharp front in a condensation shock. In the supersonic expansion part of wind tunnels, those condensation shocks are weak detonations. All of the shock tube experiments that Professor Ramsey talked about, if they are exothermic, in principle are strong detonations, very strong detonations, because the heat release is so small behind the shock wave so strong detonations are achievable. It's possible, and people have, for example, in expansion parts, by having a reacting mixture expanding through a converging, diverging nozzle to establish a normal shock wave in the diverging section, and have exothermic chemistry behind that shock wave, and so that then would be an example of a standing detonation, which is a strong detonation. But for most situations where the detonations are started by say a spark at the end of the tube, and then the deflagration develops, and there's a transition to detonation. Detonations propagating in tubes or in typical detonation experimental situations, the strong detonation is weakened into the Chapman-Jouguet point, and so they are so Chapman-Jouguet detonations are typical detonations. When people talk about detonations, often they're thinking only about Chapman-Jouguet detonations. So that's a long answer to a short question. Any other questions about yes?
What is the physical meaning of Chapman-Jouguet point?
The physical meaning of what?
Chapman-Jouguet point.
Chapman-Jouguet point.
Yeah.
I mean, mathematically, it's the intersection, the tangency condition of the Rayleigh line and the Hugoniot. The general structure of a Chapman-Jouguet detonation is very much like the general structure of a strong detonation. And so in that sense, it's not special physically, but it's special physically in that the wave dynamics associated with propagation of detonations is that there's a tendency for a strong detonation to evolve as it propagates into a Chapman-Jouguet detonation. So that's, and I'll be looking at that, at how that happens. Any other questions at this stage? Or, okay. Well, then, in order to see this is a summary of what I've just been saying. In order to see what the structure of these waves, these light waves would be, it's helpful to introduce simplified models. There's these slides will have 10 specific, and also the associated reading material have 10 specific assumptions that lead to simplified models for describing detonation structure. The maximum simplification can reduce to three non-dimensional three non-dimensional variables for now. So now we're adding the viscous term into the momentum conservation equation, and we're also adding heat conduction and viscous dissipation then into the energy conservation equation, and then diffusion now, looking in the interior of the way, is included in the species conservation equation. In this equation, epsilon I is the can you see this? Epsilon. Can anybody see this? Is the mass per unit volume of species I times the average velocity plus the diffusion velocity of species I, divided by the total flow rate per unit, and so we use yi as the mass. You remember fraction of species I, and this is the mass flux fraction of species I. And so people don't usually introduce mass flux fractions, but it's useful because it takes into account the diffusion velocity of the species as well as its convection by the mass average velocity of the mixture, this mass flux fraction. It has the same properties as the mass fraction, that it sums over all species to 1, but by definition, but whereas all mass fractions are positive, it's not always true that all mass flux fractions are positive. Some can be positive, some can be negative. In a diffusion flame, different species, even if it's one-dimensional, diffuse in different directions. So people tend not to introduce this, although it was introduced in the 1954 paper of von Karman. So you usually don't find that in textbooks, but 1954 paper of von Karman and Penner on laminar flame structure. And the book by Penner, it's an old book, but it's Chemistry Problems in Jet Propulsion. Is the title of it. And in discussing flames, he works with the mass flux fractions, and they're useful in this context as well. Okay, one reason that it may be useful is that if you have, say, a reaction, a chemistry that you write as reactants going to products, and you define a quantity which is you define it, say, a reaction progress variable. We called reaction progress variables epsilon before. Reaction progress variable would be like the flux fraction of the product species minus the flux fraction of the product species in the initial mixture divided by the flux fraction of the product species in the final mixture minus the flux fraction of the product species in the initial fracture. This goes from 0 to 1, 0 initially, 1 finally, and pretty clear from this equation, then it measures it's a measure of the extent of the reaction in going from reactants to products. So it's a non-dimensional normalized reaction progress variable. So these flux fractions are useful simply because in the species conservation equation they get rid of the they get rid of the complication of the diffusion velocities. They take that into account just automatically. If you look at the energy conservation equation, which is here, then that comes out, that involves both chemical and thermal enthalpies, but it also involves kinetic energy in this way. And so another normalized variable besides this reaction progress variable epsilon that's useful is the non-dimensional or normalized stagnation enthalpy. Variable, and I denote that by tau. So tau would be CPT plus b squared over 2, the thermal enthalpy, thermal stagnation enthalpy because of including the velocity, minus the initial value of that. And then normalized to go from 0 to 1, just like epsilon, Cp T infinity minus V infinity squared over 2, minus Cp T naught plus V naught squared over 2. Okay? So it's helpful to work with those two normalized variables for the reaction progress and the that's what I just wrote down. Yeah. Now, this third variable that can use that introduces just the velocity, and they're not non-dimensionalized by the initial velocity. C is equal to V over V naught. Okay. So that's the third variable. The momentum conservation equation, when you do this, then the momentum conservation equation can be written in this form. This is just the viscous term, and pressure forces and dynamic forces then are in this function f sub phi. That depends only on the stagnation enthalpy variable and the velocity variable. The energy conservation equation is just this. With this, to complete the non-dimensionalization, you can introduce a non-dimensional distance, which is essentially the integral of the velocity dx. This has units of so it's that has units of length squared over time divided by a characteristic diffusivity, which may vary, which does vary as inversely as rho. And so this is the non-dimensional distance that's introduced. In terms of that non-dimensional distance, then this is the form of the viscous term. This is the form of the heat conduction plus. With these approximations, the viscous dissipation term and energy conservation, this would be stagnation, thermal enthalpy, and this would be from the heat release in energy conservation. The heat release is proportional to the reaction progress. And for a one-step reaction, then this is the source, the term for the reaction progress. So the point is then, if you look at the character of these, so you just have those three ordinary differential equations, which then you can look at them in a phase plane, or in a phi, tau, a three-dimensional epsilon phase plane, okay? Phi, tau, epsilon phase plane, and look at the character of the equations. The equations have, in phase plane analysis, where the derivatives with respect to C vanish are singular points. Those singular points are then points where the singular points for this equation are points where tau is equal to epsilon. The singular points for this equation are f sub epsilon equals 0. Singular points for this are f sub phi equals 0. So the singular point for this equation, if you look at this is quadratic expression for phi as a function of tau, and so that quadratic expression has two solutions. So for tau equals 0 in the cold flow, one of the singular points is here. For tau equal, the other singular point is here. For the burnt products, for tau equal 1, one of the singular points in this projection, this is a tau phi projection, one of the singular points is here, the other singular point is here, okay? So how do these singular points determine the structure of the solution? Well, the important thing is the character of this singularity. This is a saddle point singularity, so that the curves, the integral curves expanding about this point give a saddle type behavior. This is a nodal singularity. All of the lots of curves go into that singularity. Now, so this is a saddle and this is a node. If you relate these back then to the deflagration and detonation situations, the cold boundary for a deflagration is here. This particular solution for this particular saddle point in this formulation is the cold boundary for a deflagration. The cold boundary for a detonation is here, okay? And so an integral curve then is one that goes from here, from the cold boundary to the hot boundary. This is the hot boundary for a deflagration. So a typical deflagration solution in this diagram would be one that would follow a curve like this, okay? If you don't release any heat at all, you can make a transition from one of these singular points to the other at tau equals 0. That would be going from here to here. That jump would be a shock wave. A shock wave from, so this is the cold boundary for a shock wave. This is the upstream side of the shock wave. This is the downstream side of the shock wave. For the detonation, just like when I said cold boundary for deflagration, I have to be specific. This is for a real deflagration. This is the cold boundary for a weak deflagration. Okay. For a strong deflagration, this would be the hot boundary. Okay. Now, for a strong detonation, this would be the cold boundary. This corresponds to the cold boundary. And for a weak detonation, this corresponds to a hot boundary. So when I said it goes from here to here, I'm talking about weak deflagrations. If you look at this kind of behavior, this being a saddle and this being a saddle, there is no integral curve that goes from there to there at all. So that's why I say no solution exists for the structure of the strong deflagration. That's why we don't have so strong deflagrations. There are lots of curves that go from here to here, so there are lots of possibilities for strong detonations. There are many different possible, from almost any point, lots of different structures for strong detonations. For weak detonations, the situation is just like going from here to here is going from a node saddle relation, just like for a deflagration node saddle. So the laminar flame problem for deflagrations is an eigenvalue problem. Solutions exist only once you satisfy the cold boundary once you circumvent the cold boundary difficulty, which Professor Seshadri discussed. There is just one deflagration velocity for which you can go from here to here. Correspondingly, there would be only one velocity for which you could have a weak detonation. So condensation shocks are like deflagration in that respect. They can sit only at a particular velocity, although people haven't made use of that fact much in describing them. Whereas detonations can, and so the question is, what is the structure of this study, planar detonation? Well, is the curve like this, or is it like this, or is it like this? Which one is it likely to be? And that depends on the rate of heat release. It depends on the chemical kinetics. And the chemical kinetics tend to be such that the structure is typically very much almost this shock wave, and followed by a curve that goes from the shock gas, hot shock gas, to the final state. And that curve in this diagram turns out to be very close, almost exactly along this Rayleigh line curve. And so the solution is this, followed by some transition along there. And that's the Z and D structure of this is an attempt to show a three-dimensional rendering of what was in the previous one for typical deflagration. The starting point is always tau equal epsilon equals 0 here, and tau increases. You have to increase the temperature, actually through heat conduction processes, right? And then the reaction starts, and you go to the final state. In the detonation, these are fast waves. The viscous, the molecular transport effects are negligible, except in the lead shock. And so the molecular, so you start with a lead shock that goes down here, and then along the Rayleigh line, you release heat and come up to the final state there. It's always, tau is always greater than epsilon, has to be greater than an epsilon from the resolution of the cold boundary difficulty. So what I've just described is a structure in which there's a lead shock rather than heat conduction. It's the strong shock that heats the mixture so that it starts to react in the detonation. It's the shock wave, it's not heat conduction that does it. And then it's going so fast that the heat conduction terms are negligible, so that tau is approximately equal to epsilon along the detonation. That's the Rayleigh line condition. In a way, that means that with that kind of a structure, no matter what the chemistry is, it's a lot simpler than deflagrations, in that it's the heat release is just solving an initial value problem. You put in the shock, that heats it up, that gives you the initial condition, and you could put in chemistry as complex as you like, and you still will get, it's just a matter of forward integrating the equations of this kind for general chemical kinetics in detonation structure. So long as you adopt the Z and D, Zeldovich-Neumann, during the Zeldovich structure. It's called Z and D because Zeldovich, I did it first in Russia, and then Neumann in Princeton did it second, and Doring in Germany did it third during the Second World War period. These structures shown in the pressure volume diagram, and so this line here is the shock Hugoniot. This is a Hugoniot occur without heat release. This line here is the detonation Hugoniot, the curve with heat release. Okay. If you look at shock structure, which shocks are thin, especially these strong shocks, a few mean free pass. You really want to know what the structure of the shock is in this pressure. You don't solve the Navier-Stokes equation, solve the Boltzmann equation, because that's what gives you shock structure. It goes from here to here. This point is, this spike, this highest pressure point at the end of the shock wave is the Neumann condition. So this is the Neumann spike in detonation structure. And then, from Neumann spike, then in the first approximation, you go down along the Rayleigh line to the final state. So this would be a structure for a strong detonation. If you increase the reaction rate more and more, you start to get this sort of thing. But the physically realistic one is not EDC, but it's rather A followed by B. That's a physically realistic planar detonation structure. Okay, that looks like this. This is the structure in a physical space. The velocity decreases across the lead shock, and then as heat release takes place, the velocity increases a little bit, but the final velocity in the detonation is always less than the initial velocity. The pressure increases a lot across the shock, and then it decreases as the heat release takes place to the final. So the highest pressure, the most dangerous part of the detonation, if you like, is the pressure at the Neumann state. The Neumann state here is the highest pressure. The final detonation pressure is not as high as the initial. The reactant concentration goes down, the density goes up and down, the temperature increases across the shock enough to start the chemistry, and then that heat release continues as the temperature increases, and only when the final condition is Mach 1 does it actually decrease a little bit along the Rayleigh line. If you remember Rayleigh line solutions, as you approach Mach 1, there's transfer of kinetic energy, beyond Mach number 1 over root gamma, there's transfer of thermal energy into kinetic energy as the heat is released. Besides the heat being released, that gives that kind of a temperature profile for detonation structure. So, are there any questions about planar detonation structure now, before we go on to look at dynamics of detonations in different situations? This is the end of the discussion of detonation structure. Yes?
You described there so many variations. So is there any dimensional number or any number which will say if this number is up to this value, then I will get a Hugoniot curve or Rayleigh curve, or detonation will be strong detonation or weak detonation? So it's like if I have a case, initial value is P and V, then how do I know that which kind of behavior the system is going to show?
You mean, are you asking whether it will be a deflagration or a detonation?
Yeah.
Well, it depends on how you set it up, on the dynamics of the situation, okay? I mean, it depends on the particular experiment. There's you can't just identify a number. You have to define an experiment to know whether you're going to get a deflagration or detonation. Some experiments you get deflagrations, others you get detonations. If you spark a gas just with a spark, it doesn't directly go to a detonation unless the spark is extremely strong. If the spark is extremely strong, you can have a direct initiation of detonation. The last view graph is the requirement for direct initiation of detonation.
So like in practical problems, if I have a system and I want to know which kind of deflagration or which kind of waves which will be there in the system, is there any way we can know a priori what kind of, so like there are some positions in which the shock wave is such that the pressure is so high that my system may fail. So are there any ways to know a priori that my system may fail and design the system as such?
Yes. Yes. I guess the point is that it's not easy to establish a detonation right off. You can't. You have to deposit an awful lot of energy. So if you deposit enough energy instantaneously, then you can make. Then you can go to a detonation. But most likely, any ignition source is going to give you a deflagration, not a detonation. So you'll start with a deflagration. And then the deflagration, like, for example, would propagate. If you start with a spark, in a tube, the deflagration will propagate down the tube. and it can develop. It typically develops turbulent flow. The velocities give you shear layers which are high enough to make transitions to turbulence. The turbulent flow increases the deflagration velocity from laminar deflagration velocity to turbulent deflagration velocity, and eventually gets high enough, and pressure waves then are developed. The stronger the deflagration, the greater the pressure difference is between reactant and product. Pressure waves are then generated. They propagate, they reflect, and then typically typically at the wall, a point will get hot enough that you have that you would have a hot spot that would now give you strong enough shock waves, strong enough pressure waves to make this temperature high enough that now the reaction rates are high enough, and then this develops into non-planar detonation, which eventually is a planar detonation propagating down the tube. So it's this is the deflagration to detonation transition process, which is a pretty complicated process that people are still studying, but that's the typical way that detonation would develop. In a shock tube experiment, you start the shock wave initiates the exothermic chemistry. So in a shock tube, that's what I'm saying. It's a matter of interpretation. In a shock wave, in a shock tube, the reaction process is really a strong detonation, but it's so strong that really you've established the shock just by the shock tube itself, and the chemistry is really not influencing the propagation speed at all. The chemistry influences the propagation speed of the detonation at the Chapman-Jouguet point. Well, even there, it's not chemistry, is it? Because it's the Chapman-Jouguet condition. So in a way, chemistry doesn't influence the propagation speeds of detonations. They're determined by these conservation conditions. That's too long an answer again. Yes.
Phase plot, you have not indicated any direction. Is there any specific reason you have not indicated any direction, whether it is a stable node or an unstable node?
Yeah, I didn't indicate direction. The initial one is unstable and the final one is stable, and so if you look at the dφ dt, this is an unstable node. Well, in that as time increases, it moves in this direction. This is the final state is a stable node. So this is a stable node. Any other? Yeah. Yes.
The ZND structure. The ZND structure helps us to find out the ZND structure helps us to find out the structure only for Chapman-Jouguet detonations or even for strong or weak detonations.
I didn't hear.
The ZND structure is helpful for finding the structure of only Chapman-Jouguet detonations, or
everything I was talking about is the structure of strong detonations and Chapman-Jouguet detonations. Weak detonation structure would have to be quite different. Weak detonation is not preceded by a shock wave. Okay. So weak detonations are really not combustion processes. They're condensation shocks. Sometimes in complex geometries, for example, or in chambers with baffles or detonations can propagate at velocities that are less than the Chapman-Jouguet velocities. They're slower detonations, but they are, combustion waves, detonations. So, and some people call them weak detonations, but that's not the kind of weak detonation. That's entirely different than my terminology here for weak detonation. Yeah. So, what I called weak detonation here is not something that we would be interested in combustion. Okay. So, anything else at this stage? Okay, then let's try to get on to the question of
Hello?
oh, I'm sorry, there's another one?
One
Oh,
more question.
yeah.
What is the meaning of the singular line? Like in the graph you were showing, what is the physical significance of singular line? So what do they signify? Is it the point where the deflagration and detonation they mix or what?
These are the singular points are the initial state, the fresh gas, and the final state, the burnt mixture. There's a whole singular line, as you say, but the dynamics avoids that line, except at the initial and final conditions, because, for example, we have d tau dc is tau minus epsilon. Yeah. Tau is greater than tau increases. Tau is greater than epsilon. So along the singular line, tau would be equal to epsilon. The point is then, if you look at d phi d tau, that is d tau d c would be this f sub phi of tau and phi divided by yeah. Well, I'm sorry. Well, it depends on what we're talking about. But suppose I have tau equal epsilon, and so that d tau d epsilon d tau d c is the same thing as the epsilon d c. So it's really this f sub epsilon, which under those conditions is a function of tau and phi. So a classical phase plane analysis would have this derivative equal to the ratio of something to something. And if that's equal to 0 and that's equal to 0, then you have 0 over 0, and that's the definition of the singularity. And so where the slope is in the phase plane is not determined, so it's not a physical thing, but it's a mathematical thing in the phase plane. So the singularity is where the slope is not determined. Physically, in our cases, it's the initial or final condition. Okay?
You're saying that tau is equal to phi, which means that my reaction progress and the stagnation, that is the flame is progressing at the same speed. Like wherever my reaction is happening, there my flame is there. So tau is equal to psi, means the normalized stagnation enthalpy and my reaction progress variable, they both are equal.
Yeah, this is true in the detonation, yeah. This, if you like, is a Rayleigh line. So if you're on the Rayleigh line, then you're on a, that's where that happens. So that's the Rayleigh line part of the detonation. All I'm saying is that you ask about the physical significance of the of these singular points, and in a mathematical sense, it's not a physical, but it's a mathematical sense where you have numerator is 0 and denominator is 0 in phase plane analysis. In the physical sense, it's only the initial and final conditions that for which these occur. And it was only the initial and final conditions that we saw, those singular planes. So either it's either fresh, physically it's just a fresh gas or the burnt mixture. Okay, I think we should move on at this stage because there are a number of other things that we really should look at, like the dynamics of wave propagation in tubes. Okay, so suppose I have a detonation now. I've done this experiment. I've initiated the wave and it's propagated down the tube. So let me look at wave detonation propagation in the tube, but let me look at it in a coordinate system in which I'm moving with the wave. Okay. So in that coordinate system, the gas ahead is moving into the detonation at velocity v0. Okay. So this is upstream from the detonation as seen from the detonation, and this is downstream from the detonation. Okay. And so so in the detonation frame of reference, the gas is moving in at this detonation velocity v0. Then the detonation occurs, the velocity decreases we saw, and then increases a little bit through the detonation. Now this is the end of the detonation. In this experiment, in the coordinate system, we're moving with the detonation. The laboratory is moving past me at detonation velocity, and that means in my coordinate system, the end of the tube is moving past me at detonation velocity. And so when I get to the end of the tube, I have to be back to detonation velocity, and so there must be a velocity profile like this in the tube behind the detonation. Now, a velocity profile like this is a rarefaction wave. The pressure here is greater than the pressure there. If it's isentropic, it's rarefaction. The rarefaction waves are acoustic waves. They propagate at acoustic velocity. And so if the velocity here with respect to the detonation is subsonic, then this rarefaction will catch up with the detonation, and it can weaken it. One of the aspects that I forgot to mention about detonation structure is that for strong detonations, the Mach number at the end of the detonation is subsonic. For weak detonations, it's supersonic. For Chapman-Jouguet detonations, it's unity. And so what would happen is that this rarefaction wave can catch up to detonation, it can weaken it, and it can continue to weaken it until it gets to the Chapman-Jouguet point. Chapman-Jouguet point, the Mach number is unity in this coordinate system, and so the detonation can no longer see this rarefaction wave, And so it will continue to propagate at Chapman-Jouguet speed. That's why in a tube experiment, to answer an earlier question, then detonations propagate is for this wave dynamic reason, and it's not for a structural reason, but it's for a wave dynamic reason in the environment in which the detonation is moving. Is that okay? Is that an okay answer to your question? Okay. Anything unclear about that point? There can be a complication. Hugoniot are different depending on whether you let the reactions go to equilibrium or whether you freeze them at the final state. If you freeze the reaction to the final state, you get Hugoniot curves that are frozen Hugoniots like this. And there's been the debate long ago in the literature as to whether the intersection between the Rayleigh line, the tangency condition for this Chapman-Jouguet condition, whether it should be applied to the equilibrium Hugoniot or to the frozen Hugoniot at the equilibrium state. And it's wrong to apply it at the frozen. It's right to apply it at the equilibrium. Because this process starts with a strong detonation. A strong detonation is, there's a shock with a Neumann state with the pressure then decreasing. The point is that here you would reach the strong detonation. This intersection is on the weak detonation branch of the equilibrium Hugoniot, and so you can't really get to point C. You can only get, so it will weaken it from this strong point D down to the Chapman-Jouguet. So the point is you should be using equilibrium Hugoniots in calculating detonation velocities. Detonation velocity is simply determined by m, the slope of the Rayleigh line at the tangent case, and so that's why you can calculate detonation velocity so simply. Any questions about that? Here. A little bit more about detonation dynamics, okay? The same idea now. This detonation is propagating down the tube, right? But there's a boundary layer at the wall of the tube, okay? And so, again, in this same coordinate system, moving with the detonation, not only is the incoming gas coming at the detonation velocity, but the wall of the tube also is zooming by the detonation at the detonation velocity, because the wall of the tube is thick. And so there's a velocity profile, which is not your usual velocity profile that Professor Seshadri showed in his first lecture, but rather it's the opposite way. The velocity is greater in the boundary layer than it is in the free stream when a detonation is going down the tube steadily. What does that mean? That means there's a mass flux. There's mass flux here is greater than there. The mass flux from the detonation into the boundary layer. That leads to the detonation being curved instead of planar, and so detonations propagating in tubes tend to be curved. And that has an effect of two-diameter detonation propagation velocity. The change in this is the theoretical infinite tube diameter detonation velocity. Empirical, there's a decrease in the detonation velocity associated with that effect. Okay, I do I do want to say something about stability of detonations, and it would really be nice if I had another half an hour. I'm in the same trouble that everybody, all the other speakers have been in, running out of time to cover all of this. So so far we've been looking then at detonation structure and dynamics. Are these detonations stable, or are they not? Are they unstable? There are really two kinds of processes that can lead to instability of detonations. One is a purely planar process, where the detonation, and that's an effect of the chemical heat release, of the rate of heat release depending strongly on the temperature, and that can lead to an oscillatory type of behavior, so-called galloping detonation behavior. But besides that effect, there's a non-planar instability in which vorticity plays a role, and so there's a chain, and so as long ago as 1961, somebody by the name of Erpenbeck did analyses of, say, planar and also non-planar detonation stability, and he found that even if the heat release is small, small compared with the initial thermal enthalpy, then this non-planar mode is unstable, and so the instability to non-planar disturbances is stronger than the instability to planar disturbances. For planar disturbances, you can do an analysis in which you can approximate, a good approximation for the detonation structure is a two-zone structure. So there's a shock wave, this is velocity versus distance, an induction zone, and it takes a while for the chemistry to get going, and then there's a reaction zone, a heat release zone, okay? Induction, heat release, or reaction. They tend to be roughly the same size as when you do that calculation detonation structure for Z and D, as but you can get an understanding by assuming that this is that the heat release takes place rapidly. If you assume that the heat release takes place rapidly, then if you have make a perturbation to the detonation velocity, say a delta V naught, there's a corresponding perturbation to the Neumann velocity, to the velocity at the Neumann state. Well, the length of the induction zone is this velocity at the Neumann state times the induction time. And the induction time is really very much like what Professor Seshadri's thermal explosion time. And so the induction time decreases very rapidly as the temperature increases. And well, so in increase in this velocity will give an increase in the Neumann velocity, but also increase the temperature. The temperature is proportional to the Mach number squared, so twice as much. It will increase the temperature, and so by increasing the temperature, it's decreasing this auto-ignition time. The decreased auto-ignition time then shortens the induction zone, and so the heat release now is moving closer here. And has the same effect as a piston moving here. And so a perturbation like this will give rise to a piston effect. So there's there's a time for this convection of the temperature perturbation through the induction zone to reach the heat release zone. When it does, it increases the temperature and causes so there's a convective motion in that direction, followed by, this is subsonic flow, an acoustic wave. And so the velocity of the wave going backward is the sound speed minus the Neumann speed. There's a period of oscillation that you can calculate then for a pulsating detonation, galloping detonations, which is roughly 10 times the, when you put in numbers, 10 times the induction zone length divided by well, in this case, the propagation velocity is written that way. This is an approximation for strong shocks, and typical detonations have shocks that are in the strong shock limit. And so this is an estimate for the cellular, for the propagation frequency of detonations. What did I do? That was backwards. Yeah. Propagation frequency of detonations. And so that would be for galloping detonations. This non-planar instability is stronger, and the typical structure of the non-planar instability is the triple point structure. It develops nonlinearly into what's an incident shock, a transmitted or Mach stem shock, and a reflected shock with a slipstream behind. And the highest temperature change is across the Mach reflection. Most of the heat release is there. The highest pressure is at the triple point. And so if you put smoked foil on the walls of a tube and send a detonation down the tube, you see this diamond pattern develops. And the diamond pattern is cellular detonation. All real detonations, at least Chapman-Jouguet detonations, this is not applied to the strong detonation in shock tube, but real detonations in tubes are unstable because of the high activation energy of the induction process, the effective high activation energy, and they for these diamond patterns, which are well known, could have been discovered in 1935, but where people found spinning detonations at low pressures, but were not discovered until diagnostic techniques got better. In the 50s, people started to see what they called turbulent detonations, and then they expanded and saw the structure of the turbines was not really turbulent, but is very irregular in many cases, giving these regular diamond patterns with some spacing between the diamond patterns. The spacing is roughly 13 times the induction zone length, experimentally and computationally as well. This number 13 comes up in detonations. It seems to be a magic number in detonations. Cell sizes of cellular detonations are 13 times as large as and the number can be calculated in terms of gamma, typical values of gamma, by looking at 13 times as large as the induction time. And also in other experiments where you want to send a detonation out of a tube into the same gas, a detonable gas, the tube diameter has to be large enough. Otherwise, the detonation is not going to be transmitted from the tube into the opening. Detonations are favored by having confinement, and so confinement helps to confine the detonation, and again, experimentally, it takes about 13 cells across the diameter of the tube has to be big enough to fit 13 cells in order for the detonation to transmit into a spherical detonation outside the tube. So that 13 is the magic detonation number. Then the last two things here are detonation failure and direct initiation of detonation. I did mention in answer to one of the questions that detonations could be generated directly by depositing enough energy instantaneously, and depending on whether it's 1, 2, or 3 dimensions, energy per unit area, or energy per unit volume, deposited. There's this formula in terms of the detonation velocity and the induction time and there have been, this is experimental, and there also have been analyses of direct initiation. I would say that there still is research on direct initiation of detonation even, and there's some deficiencies in describing that. So as far as detonation failure, the point is that if the net volt region is small enough, and you have an inert gas on the other side of it, say, then this detonation propagation will generate an oblique shock in the inert gas. Across that oblique shock, there's a flow deflection. The flow deflection is an area expansion. There's a competition between area expansion then and heat release. Area expansion in subsonic flow behind the shock wave, this is what this flow is. Area expansion and subsonic flow behind the shock wave decreases the Mach number, whereas the heat release increases the Mach number, and you have to increase it at least to the choking point, Mach 1, to complete the detonation. So if the area expansion is too large, it prevents that from happening. So there no longer is a solution for the structure of the detonation. And so if this layer is too thin, then the detonation will fail. And so there are approximations then for detonation failure that are discussed in the reading material for the course, and it leads to, in terms of the hydraulic diameter, it leads to expressions for tube diameters, the corresponding effect of the expansion due to the flow from the free stream into the boundary layer in the tube that lead to detonation failure. So there are detonation failure conditions as well. The only thing I would finally say is that there's a really definitive book will come out. The title will be next year by Clavan and Searby. It will be the title of Cambridge Press, Combustion Waves and Fronts and Flows. If you're interested in this subject, this will be a source of definitive up-to-date material on not only on detonations, flame shocks, but especially on the detonation phenomena that I've been talking about here. So I had to rush, and I actually went 5 minutes over, but it seems to be traditional that we do that. But are there any questions at this stage about any of this material? Yes.
Is there any particular reason why detonations in tubes don't follow no-slip boundary condition?
Why what?
So is there any reason why detonations in tubes, they don't follow no-slip boundary condition?
They do follow no-slip boundary conditions, but I mean, the front is not, that's the whole reason for the, that's the whole reason for this picture. I mean, this is a no-slip boundary condition, okay? This is a no-slip boundary condition because it's in the coordinate system moving with the detonation. So if I sit on the detonation, then the tube is moving by at that velocity. The no-slip boundary condition gives me that, okay? Good enough? Yeah. Yes.
In that case, why the V is less than V? I mean, why the velocities in the reaction?
The question is why is this V less than V0, and this is V0 and this is V infinity. This is the velocity behind the detonation, okay? And so V infinity is this is V0, and V infinity in the detonation structure. The jump condition, if you want to go back to all the way to the Rankine-Hugoniot condition, the jump condition, this is 1 over. This, if you like, is V, because this would be V0, and this would be this value would be V infinity, just from the jump conditions across the.
I have one more question. In a typical isentropic flow, if there is a diverging nozzle, the Mach number increases through the nozzle, right? If there is a diverging nozzle for a supersonic flow.
Yes, but this is subsonic. So it goes the other way.
So if a shock wave is favored in a converging nozzle, right, compared to.
Yes.
So
Yes.
what will be the diverging nozzles? Is it because it becomes subsonic and it gets
Oh, are you talking about about the standing detonation?
Yeah, standing detonation.
Yeah. Well, first of all, to have something. First of all, these detonations propagate at supersonic. All of these velocities are supersonic. The tangent condition is sonic. This is subsonic. So detonations all propagate at supersonic velocities. So in order to have a detonation standing there, you got to have supersonic flow coming into it, right? In the converging section of an isentropic nozzle, you have subsonic flow, so you have to be in the diverging section, which is the supersonic flow. Okay, supersonic. And that's only in that case that you can establish the detonation. What it looks like is that you can have set the back pressure so that you have this kind of a structure in the central part. This Mach number is greater than 1 because it's and you can have a detonation then go across which. So it's this kind of an experiment that would result in a standing detonation. Those experiments were done at Michigan in the 50s, for example.
One more question is regarding the upper Chapman-Jouguet point. In general, the detonation waves are represented by the upper CJ point, right? And in most of the textbooks, they give an explanation for the inexistence of the remaining solution, remaining part of the curve. by stating that the entropy increases in those cases and the second law is violated.
Yeah,
Yeah,
they're wrong.
Yeah, I mean,
They're wrong, okay?
yeah, so is there any detailed explanation? They just state that the entropy increases, so
Yeah.
what is the physical
Well, you can
interpretation of that?
calculate, yeah, it depends on what, yeah. If you go along I forget which way it goes. If you go along the Rayleigh line and calculate entropy as a function of distance along the Rayleigh line, it's a maximum at the Chapman-Jouguet point, or maybe a minimum. If you go along the Hugoniot, it's a minimum at that point, or maybe a maximum. I forgot which. So what entropy condition are you using? Maximum entropy or minimum entropy? Depends on what you line. It's just not reasonable. It has nothing to do with the reason why. I explained the reason why the detonations use. It's for a dynamic reason. It's not for any reason that you calculate from thermodynamics by looking at entropy.
Thank you.
Okay.
I have one question. The cellular cells, what you have shown, they are formed. The cellular cells, shock
Yes.
cells, that they are formed only in a tube, or what we see the shock diamond, what we see in the exhaust of rockets or jet fighter jets, we see some cellular structure at the exhaust. Are they same or are they different?
They're different. In the exhaust of rockets, you don't have, the reactions are not negligible, are negligible. And so that's a different gas dynamic phenomenon where you've either overexpanded or underexpanded. And so if you overexpand, then you get these oblique shocks which interact, and when the oblique shock they reflect as expansion waves which overreact, and so you get that diamond pattern in the exhaust. But these are purely gas dynamic effects in the exhaust, whereas the cellular detonation is what's, well, if this is strong enough, then it's not cellular. But if this becomes close enough to Chapman-Jouguet, then this is really not exactly a plane, but it has some cellular structure to it of the kind that you see with the markings on the wall.
Yeah, thanks.
So all you had to do to see that there are cellular, all they had to do to see that there were cellular detonation was to read the writing on the walls, and it took them 25 years to do that, from the 30s to the 50s. Anyway.
Excuse me, sir. Excuse me, sir.
Yes.
Sir, if we see the equations across a shock with heat addition, then if we plot it on a Mollier diagram, then we see that for a subsonic flow, heat addition leads to Mach number 1, where it gets thermally choked.
Yes.
And then if I compare that with this situation, then this is also a shock with a heat addition behind the shock. And for a Chapman-Jouguet condition, it also reaches a Mach number of exactly 1.
Yes.
So are the two related?
Yes. It's the same thing. Yeah.
But then the heat addition is independent, right? It depends on the chemistry.
The rate of heat addition depends on the chemistry. Yeah.
So from a gas dynamic point of view, it is reaching a Mach number 1, or from a chemistry point of view, it is reaching Mach number 1?
Well, from a chemistry point of view, you're releasing enough heat eventually to make the gas dynamics go to Mach number 1, and it's both chemistry and gas dynamics.
No, if I take a very strong mixture, then it is possible that the heat addition is so high that it may actually cross Mach number 1 and come back to subsonic.
No, you can't do that. No, it's a choking condition, gas dynamics, Mach number 1. You can't go past Mach number 1. If to go past Mach number 1, gas dynamically, you have to take heat out to go on the lower branch of the Rayleigh line.